Mastering this topic sounds complicated, but it doesn't have to be. In this video, we're breaking down exactly what you need to know, step by step, with zero fluff. Let's get right into it.
A black hole acts as the universe's ultimate one-way street. It is a region of space-time so dense that any matter or light crossing its threshold is swallowed permanently, dragged toward a center from which nothing escapes. This inescapable nature creates a problem for the very equations that predict their existence. The laws of general relativity do not actually distinguish between the past and the future. These laws are time reversal invariant. If you take a valid solution to Einstein's equations and flip the time variable t to a negative t, the physics remain perfectly consistent. Running the math of a black hole in reverse produces an unavoidable consequence. If the equations allow for an inescapable gravitational sink, they also demand a gravitational fountain, a white hole that constantly ejects matter into space. The mathematical certainty of these objects creates a tension with our observations, as we have never actually seen a white hole in the physical universe. To find where a white hole fits into the cosmos, physicists use Kruskal-Sakaris coordinates. This specific geometry allows them to map the full theoretical extent of a static black hole. This maps region 1, our universe, and region 2, the black hole interior. Mathematically, this model is only half the picture. The complete solution requires a symmetrical lower half, region 3, a parallel space, and region 4, the white hole, connected by a wormhole. The mechanics of region 4 are the exact inverse of a black hole. Here, a past singularity erupts, streaming light and matter outward across an event horizon. You cannot enter a white hole from the outside because its outer boundary is expanding at the speed of light. To cross into it, a ship would have to travel faster than light itself. In a purely mathematical, static universe, black holes and white holes exist in perfect, impenetrable harmony. But physical reality is rarely so neat. While math permits their existence, the physical laws of the universe actively work to destroy them. The first obstacle is the second law of thermodynamics, which dictates that entropy, or disorder, must increase over time. A white hole violates this arrow of time. It takes the crushed, chaotic matter of a singularity and spontaneously organizes it into macroscopic matter as it spews into space. Even ignoring thermodynamics, white holes are unstable and cannot survive surrounding matter. If a single photon falls toward a white hole, it encounters outgoing matter and undergoes an infinite blue shift. This massive energy gain creates a pileup at the horizon. This energy surge instantly collapses the white hole's horizon, transforming the entire system back into a standard black hole. Because they violate the laws of entropy and self-destruct upon contact with light, macroscopic white holes remain a physical impossibility. Reality overrules the chalkboard. Einstein's mathematics likely hold up, provided we look at the right physical scale. Modern physicists like Carlo Rovelli use a theory called loop quantum gravity to suggest a different fate for collapsing stars. They propose that a star doesn't shrink forever. Instead, it reaches the Planck length, the absolute smallest limit allowed by physics. At this point, it becomes a Planck star. When the star hits this minimum limit, quantum pressures cause it to experience a quantum bounce, pushing back against the force of gravity. This bounce triggers a quantum tunneling event, where the dying black hole transitions into a microscopic white hole. This microscopic explosion releases all the matter and information trapped inside the black hole, returning it to the wider universe. The black hole represents the first stage of a cosmic life cycle, while the white hole is the microscopic burst that marks its end.